the analogy that astronomers use, no analogy is perfect, right? We're dealing with things, not just in the 3 dimensions of space, but in the 4th dimension of what we call space-time. So we have to visualize things that are really unvisualizable by the human mind, by our own limitations. And so we make analogies. So one of the most common analogies is to think about, I'll give you 2. One is to imagine a balloon with little dots drawn on the balloon's surface. The balloon surface is 2-dimensional. As you blow up the balloon, the galaxies move away. The dots on the balloon surface move from one another. And they move with exactly that property, that a galaxy that is 1 centimeter, or a dot that's 1 centimeter away from another galaxy, or dot, will move twice as much in the same amount of inflation or expansion as a galaxy that is half a centimeter separated, or a dot, 2 dots that are only 5 millimeters apart from one another. But that's confined to a 2-dimensional surface, so it's a little bit hard to maybe project that into 3 dimensions in our mind. So another one that people use is, imagine baking a raisin bread. So a bread, and you put in a bunch of raisins inside of it. That too has the exact same property. If you sit on any raisin inside the bread and you watch, what are the other raisins doing? They all will be observed to move away from you. There won't be any gravitational attraction between you and another raisin. So you'll actually observe what's like a perfect expansion of the universe from your perspective. Remember, I said there are about 20 or more galaxies that are gravitationally attracted to the Milky Way, and they are blue shifted because they're falling towards us and will eventually combine into an enormous mega galaxy called Milkdromeda someday. But that doesn't happen for raisins or for dots in a balloon. So the law that describes that type of expansion in either a raisin bread populated with raisins in 3 dimensions, or a balloon dotted with magic marker marks in 2 dimensions, those two phenomena are exactly displaying what's called Hubble's law, which is the velocity of every galaxy we see beyond a certain distance. That's a minimal distance that we don't have gravitational interactions between us and them. That galaxy will be moving away directly proportional to what's known as Hubble's constant. So the velocity in meters per second, miles per hour, furlongs per decade, whatever you want, will be directly linear. It's the simplest law imaginable besides just a constant. It'll be moving linearly proportionate to its distance away from you. And that's a fascinating observation. And that's the only type of observation that can produce the type of structures that we see in the universe. In other words, it could have been traveling as the velocity scaling as the square of the distance, the cube of the distance, the square root of the distance, whatever. We would live in a much, much different universe, and it wouldn't have any of the characteristics that we observe.
So I think when I read Stephen Hawking's Brief History of Time, which is, it's got to be 20 years ago or approximately.
Oh, it's 40, almost 40 years old, yeah.
Is it? God, well, that's what happens when you get old. The decades start to collapse. So at that point, my memory, if my memory serves me properly, the standard cosmological model was that it emerged from a Big Bang and that the universe was expanding, but that at some point it would contract back on itself, and this was Hawking's idea anyways, and then collapse back down into another singularity, whatever existed before the Big Bang. But it's my understanding that over the last few decades, the evidence has accrued in an incontrovertible manner that the rate of expansion is actually increasing rather than decreasing. And I believe that's the great mystery that's propelled scientists to posit the existence of such phenomena as dark energy. Have I got that right? And what's the current state of thought about the fact that, first of all, explain why that's surprising, that the rate of increase or the rate of expansion is increasing. Explain why that's surprising. And then would you explain how that view has changed over time and where we're at now?
Absolutely, yeah. So I got to hear Stephen Hawking speak at the Royal Astronomical Society meeting in London in 1995. And it was back when he couldn't speak for a very long time. So he wasn't able to actually speak in real time, but he could move his fingers and he could move his eyes and he could type on this very special keyboard, which the ex-husband of his current nurse at the time had invented. That's a whole other story. I can recommend a book by my friend Charles Seif called Hawking, and it was sort of the business of Stephen Hawking. And he could answer one question, and it would take him about 10 minutes to answer a question. Someone asked him in the audience, Professor Hawking, you're rumored to be the most brilliant man alive, and yet you've written this book that almost no one, besides a younger Jordan Peterson perhaps, had read cover to cover. Why did you write this book? And he answered in his computerized synthetic voice, because my daughter needed to pay for college. And it was just interesting that this great man, this great intellect, trapped in this body that had, been robbed of all of its physical kind of maneuvering and so forth, was so facile with his mind. It was really an incredible thing to see. When Hawking wrote that book, it is true. The expectation was that the universe would eventually collapse on itself, would eventually undergo what's called a big crunch, which is essentially the opposite of the Big Bang. We would observe, if we were living billions of years hence, the story went, that we would see not galaxies being redshifted, but galaxies being blue shifted, because we're all going to combine and eventually into a collapse of an enormous, if you like, gravitational time bomb that would probably play out over, billions, if not trillions of years. So I kept advising people to keep paying their taxes. But at the time, we didn't know about this substance called dark energy. And what's so surprising about that, and what kept Einstein really flummoxed for the first part of his career, was that we only knew of a few different forms of matter and energy in the universe. We knew of matter, stuff, the stuff that we're made up of, and we knew of light. And in a universe that only has matter and light, it's impossible to not have a gravitational collapse. Just as the same is true if I take an object, a ball or an apple, and I throw it up at some velocity, it will still come back down unless it reaches what's called escape velocity. And the perplexing thing about Einsteinian general relativistic gravitation that still mystifies me and experts is that when you add matter to the universe, it actually makes it expand faster, which is counterintuitive. You would think if there was more gravity in the Earth's surface, the apple would actually fall down even quicker, which it would. But in the case of when we describe the expansion of the universe, we're talking about its velocity, not its acceleration. So there's a crucial distinction. The universe can have objects moving faster away from each other, and that doesn't involve necessarily their acceleration. So what Einstein did to counteract that fact, he was a pretty smart guy, right? He looked around and he said, well, the universe doesn't seem to be collapsing, so there must be some hidden form of energy that we don't observe. And that unobserved matter he called the cosmological term, or cosmological energy source. We later called it the cosmological constant, and now we call it dark energy, as you proposed. What that does is by adding in matter, you get anti-gravity, or you add in energy, pure energy, you get a form of anti-gravity. Almost as if, it's the comic book hero's dream that you could suspend gravity, that you could freeze the motion of objects that tend to want to combine with one another. So he then had a mechanism, contrived as it was, to explain why the universe appeared static, as it did in 1920 and 1919. But then, as I mentioned earlier, when Hubble observed the universe is in fact not static, Herr Einstein, the universe is expanding, then Einstein had the brilliance, the humility, and the confidence to say, I was wrong. And supposedly he called the insertion of the cosmological term his biggest blunder.
Right,
now,
right. So he was trying to account for the fact, let's just to get the chronology clear, at that point, the universe appeared static, and Einstein was trying to figure out why it wasn't collapsing onto itself. And so he proposed a constant which you equated to something like an anti-gravity energy. But then the problem turned out to be even worse than it seemed to be, because it was not only not collapsing not static and not collapsing, it was expanding. Yeah. And that's the mystery that people are trying to address, still today, with the hypothesis of something approximating dark energy.
That's right. So the dark energy phenomenon causes not only a reversal of the collapse of the universe's infall of all these galaxies or raisins or that would be coming together. It not only freezes them in their tracks, it actually reverses that process. So instead of just expanding linearly, smoothly, as Hubble would envision us doing, actually the universe starts to accelerate. So it's as if you're pushing down on the cosmic accelerator pedal. These galaxies are not only moving apart, but tomorrow they'll be moving apart even faster. At a given distance, they'll be moving apart faster than they are. So I always joke, it was a blunder of Einstein to call that blunder his blunder, because it wasn't a blunder at all. And I always say, I like to throw in, it's too bad that he made that blunder. Otherwise, he could have had a good career. But in this case, when we look at what Einstein was conjecturing, it came back unavoidably in the late 1990s. through the observation of what are called type 1a supernovae, which are just used. It's not important to know what they are. They're exploding stars and they're fascinating objects in their own right, but they're really used as the sirens on the ambulances at great distances. So in 12 Rules for Life, you talked about the value of precision of speech. Well, the most important thing for cosmologists is precision cosmology. When I started graduate school in the 1990s, in the mid 90s, we didn't know if the universe was 10 billion years old or 20 billion years old. Now we know it's 13.824 billion years old, and we have a precision of less than 1%. And we also have an accuracy. In other words, we've calibrated that number and removed systemic contamination from that number. It's really phenomenal. I mean, at that time, we knew of objects that were older than the universe. Supposedly, there were objects called globular clusters, and they were older than the universe. That's like finding out that you're older than your mother. I mean, it's a very bizarre situation. And quite frankly, it was embarrassing to cosmologists. Now we know it with extreme precision, but with that precision comes great power. And that power allows us to assess what is the nature of this dark energy potentially. And not only that, what is it doing to our future understanding of where the universe will continue to develop in the far, far distant future. And so if the universe truly has this dark energy, chimeric form of energy, unknown, completely, unlike anything we've ever had an experience with, that type of energy will eventually drive the universe potentially in a variety of different ways, none of them good, but luckily they don't come about for tens to perhaps hundreds of billions of years. When the universe might physically rip apart, there could be aspects of space-time that at all locations develop what we call singularities, the breakdown in all the laws of physics. And certainly long before then, we will have stopped having the ability to do astronomy or cosmology. We will no longer be able to see any other galaxies after a certain point. After the universe has expanded so much, those galaxies will all be redshifted so far out of observational constraints that we won't even know we live in a galaxy. We'll just think this is the entire universe. So ironically, we'll be back to the way the state of affairs was in pre-1929 planet Earth's understanding of cosmology. And with the precision that I mentioned before, that we know the age of the universe, we know the expansion rate of the universe, we can do astounding things. We can go back in time and ask, just as we do with I remember when my children turned 2 years old, you take them to the pediatrician's office and they measure their height. And basically, they've got this rule of thumb based on the statistics of 100 billion people that have lived on planet Earth to date, that the child will be about twice as high, twice as tall as he or she is at age 2. I think I'm getting that right. I am a doctor, but I'm not that kind of a doctor, right? So you'll have to check those numbers, but they basically extrapolate. So imagine if you went and you go to the pediatrician and then you come back in 10 years, 15 years, 20 years, and the kid is like 30 times bigger than that height, or 1/10 as tall. Well, you'd say, this is crazy. There's something strange going on. Your tables are all messed up. And your actual statistical sample is not a good representation of the parent population, no pun intended. So the question becomes, how accurately can you estimate how fast the universe will be expanding today versus 13 billion years ago? And there's what's called a tension, because the two numbers disagree, and they disagree by a violently unacceptable amount. The measurements that we do with the cosmic microwave background radiation suggest a universe that is a billion years younger, if you like, than the universe that we see using the type 1a supernovae.